Alright, probability of no rain. What that is that you have no rain on the first, day 1, no rain on day 2, and no rain on day 3. Probability of no rain on any one day is 0.7, right? 70%. Since they're independent, it's 0.7 times 0.7 times 0.7. Alright, and that's, if you're working it out, 0.343, 34.3%. B was the probability of rain on all three. So rain, rain, rain. Again, independent, 0.3 times 0.3 times 0.3. The answer to that is 0.027. C, probability of rain on the first, no rain on the second, and then no rain on the third. Alright, order is given. Rain on the first, 0.3, no rain on the second, 0.7 times no rain on the third, also 0.7. Alright, and the answer to that is, if I've done it correctly, 0.147. Alright, probability of one rainy day in 3. Now we have not been specified the order, right? We don't know if the rain is on the first day or the second or the third. So we do it with number of days, number of ways rather, times the probability of one way. How many ways are there? Well, we could have either rain on day 1, day 2, or day 3, so that's 3 ways times the probability of one way, and we have one way in part C, 0.147. Alright, and the answer to that is 0.441. Alright, the last part of the problem that I gave you is something that hadn't seen before, and there's a probability of at least 1 in 3 days of rain. Alright, and that's sort of a thought problem. Alright, so think of the example that we had before with coin toss. Right, and I don't have probabilities for each of these, but if you're going to get 3 days, either you're going to have 0 days with rain, 1 day with rain, 2 days with rain, or 3 days with rain. And we have some of these probabilities, but not all of them. At least 1 in the 3. Well, at least 1 in the 3 means we could either have 1 day, or 2 days, or 3 days of rain. So what we want is the probability of 1 day, 2 days, and then 3 days with rain, and add those probabilities together. Whatever these probabilities are, we want them to be added together. Okay, we know that the total probability for this distribution is 1. So whatever this is here, let's give it a symbol. All right, let's say this probability of 0 days is W. Okay, then this here, 1, 2, or 3 days must be 1 minus W, right? Because W plus 1 minus W is equal to 1. Okay, but we have the probability of no rain. Alright, and that was the first one we did, and that's 0.343. So the answer that we want here, 1 minus 0.343, see if I can do that in my head quickly, that's 0.657. Hopefully I'm correct there. Okay, I just checked myself and I am. Okay, so the answer to this problem at least 1.657. Okay. All right, now let's go to the next topic, or subtopic, and that's sampling without replacement. All right, it's reasonably common in certain situations in the real world, but for our sampling theory down the road, we don't use this. And remember, the simple situation is candy in a jar. So let's say we have a jar of candy. We have 10 pieces of candy in the jar. They're all the same size. Alright, and let's say that we have 7 cherry and 3 lemon. So we could ask questions like the following. What's the probability of randomly selecting a cherry on the first, and a cherry on the second? Alright, the probabilities from the first to the second selection now change, okay, because we've consumed the first piece of candy after we, which is cherry, before we select the second. Alright, the way to do this probability is the probability of getting cherry in the first. Alright, so the probability of getting a cherry in the first is 7 out of 10. 7 cherries divided by 10 total pieces. Alright, and then on the second selection we're left with 9 pieces of candy, of which now 6 cherry. Alright, so this is our probability, and of course you could work that out, but at this point I don't care about the final answer, just the fact that you know that the probability changes from selection to selection, from step to step. Okay. So look at another one, probability of cherry on the first and lemon on the second. Alright, probability of cherry on the first, again, just like the above situation, 7/10. Lemon on the second, well, we're left with 9 total pieces left. 3 of those are lemon. Okay, so that's the probability. 21 divided by 90 or something. Okay. What about the probability of lemon on the first and cherry on the second? Of course, if you want to try it for yourself, you can pause the video, write it down, and restart the video to see the answer. Alright, lemon on the first. Well, there are 3 total lemon divided by 10 pieces of candy, so the probability of getting a lemon on the first draw is 3/10. Cherry on the second, well, we have 9 pieces of candy left. No cherries have been chosen at this point, so we have 7/9. Okay, now look at both these answers. Right, first we have cherry on the first, lemon second, then we have lemon first, then cherry. So when we're done, we have 1 cherry and 1 lemon. Okay, and the probabilities are the same. So on the numerator you have 7 times 3 in the first, and then in the second you have 3 times 7, but of course that's 21 in both cases, and the denominator in both cases, 10 times 9 is 90. Okay. So even though I was explicit about the order, when I'm done, the probability is the same. Right, so it's the same point as I tried to make before, but it was more difficult to make. is the probability of a head on the first and tail on the second is the same probability of head on the first, sorry, change the order, tail on the first, head on the second. Alright, change the order, the probability stays the same.